Imagine waking up tomorrow and realizing that time did not move the same way for everyone. Somewhere in the universe, someone experienced your entire lifetime in a single afternoon, while for you, decades passed like normal. This is not science fiction. This is not philosophy. This is physics. And once you understand it, you can never look at time the same way again. We grow up believing time is constant. Seconds tick forward. Minutes follow minutes. The past is gone, the future hasn't arrived, and the present is a thin slice moving forward endlessly. This idea feels so natural that we never question it. But nature does not care about what feels natural. When scientists began to measure the universe with extreme precision, they discovered something deeply unsettling. Time does not behave the same everywhere. It slows down, it speeds up, it bends, and sometimes it almost stops. For centuries, physics assumed time was absolute. Isaac Newton believed time flowed at the same rate for everyone, everywhere, regardless of motion or location. According to this view, the universe had a single universal clock ticking in the background. Every event could be placed on this timeline with perfect agreement. This assumption worked beautifully for everyday life. It explained the motion of planets, falling objects, and the mechanics of the world around us. But it was wrong. The first cracks appeared when scientists began studying light. Light behaves differently from anything else in the universe. No matter how fast you move, light always travels at the same speed. This fact seems harmless at first, but it creates a massive problem. If you chase a beam of light, classical physics says you should eventually catch up to it. Yet experiments prove this never happens. Light always moves away from you at the same speed, no matter how fast you go. To fix this contradiction, reality had to change. Space and time could no longer be rigid. They had to adapt. The universe made a shocking choice. Instead of allowing the speed of light to change, it allowed time itself to slow down. Motion affects time. The faster you move, the slower your clock ticks compared to someone standing still. This is not an illusion. This is not psychological. It is a measurable physical effect. When this idea was first proposed, it sounded absurd. How could time slow down simply because something is moving? But experiments confirmed it again and again. Particles moving near the speed of light live longer than they should. Atomic clocks placed on fast moving airplanes fall out of sync with clocks on the ground. Satellites orbiting Earth experience time differently than we do, and without correcting for this effect, GPS systems would fail within minutes. This reveals a truth that is deeply uncomfortable. There is no single time shared by the entire universe. Every observer carries their own clock, and those clocks do not always agree. What one person experiences as simultaneous events may occur at different times for someone else. The present moment is not universal. It depends on motion. This leads to an even stranger conclusion. Time is not separate from space. They are woven together into a single structure called space-time. You cannot change one without affecting the other. Move faster through space, and you move slower through time. Stay still, and time flows faster for you than for someone racing past at extreme speed. At everyday speeds, this effect is tiny. We do not notice it, because we move far too slowly. But the universe does not care about our scale. At extreme speeds, time dilation becomes dramatic. A traveler moving close to the speed of light could cross vast distances while aging only a few years. Meanwhile, decades or even centuries would pass for those left behind. This is not a theoretical loophole. It is a direct consequence of how space-time works. Motion is only part of the story. Gravity also controls time. This discovery changed physics forever. Gravity is not just a force pulling objects together. It is the bending of space-time itself. Massive objects curve the fabric of reality, and everything nearby follows that curve. Time is part of that fabric. Where gravity is stronger, time moves more slowly. This effect is not science fiction. It has been measured on Earth. Atomic clocks placed at higher altitudes tick slightly faster than clocks closer to the ground. Even a difference of a few meters is enough to detect. Time flows faster on a mountain than at sea level. The difference is tiny, but it is real. As gravity becomes stronger, the effect becomes extreme. Near massive stars, time slows significantly. Near neutron stars, it slows dramatically. And near black holes, it nearly stops. A black hole is not just a very heavy object. It is a region where space-time is curved so intensely that the normal flow of time breaks down. From far away, an object falling toward a black hole appears to slow down as it approaches the boundary. Its clock ticks slower and slower. Light from it becomes dimmer and redder. To an outside observer, the object never quite crosses the edge. It seems frozen in time, suspended forever at the threshold. But for the falling object itself, time continues normally. Seconds feel like seconds. Nothing special happens at the boundary. This disagreement is not a trick. Both experiences are correct. Time splits depending on perspective. The universe does not enforce a single timeline. It allows multiple, equally valid versions of reality. This forces us to confront a disturbing idea. If time can stretch and slow, what does that mean for the future and the past? In modern physics, space-time is often described as a four-dimensional structure. Past, present, and future all exist within it. The present moment is not something that moves forward. It is simply where you are located along your path through space-time. Another observer, moving differently or sitting in stronger gravity, slices space-time in a different way and experiences a different present. This means the flow of time may not be a fundamental feature of the universe. It may be something our brains create as they process events in sequence. Quantum physics pushes this idea even further. At the smallest scales, time behaves strangely. Some of the most important equations in physics work without time appearing at all. Cause and effect become blurred. In certain experiments, particles seem to respond to future conditions, as if the arrow of time temporarily loses its direction. These effects are subtle and controversial, but they suggest something profound. Time may not be a basic ingredient of reality. It may emerge only when many particles interact together. At the deepest level, the universe may not experience time at all. This creates a conflict at the heart of physics. Relativity treats time as flexible but continuous, shaped smoothly by motion and gravity. Quantum mechanics treats reality as probabilistic and discrete. where time sometimes disappears from the equations. A complete theory of the universe must reconcile these views, but so far, no one has succeeded. At the beginning of the universe, this conflict becomes unavoidable. The Big Bang appears to be the moment when space and time themselves came into existence. There is no meaningful before the Big Bang, because time begins there. Asking what happened before time existed is like asking what lies north of the North Pole. The question stops making sense. This suggests that time is not eternal. It had a beginning. And if it can begin, some physicists believe it could also end or transform into something unrecognizable. At the deepest level of reality, time may not flow at all. Despite how strange this sounds, these ideas are not abstract speculation. They guide real experiments. Gravitational waves detected from colliding black holes carry information about how space-time vibrates. Precision measurements of the early universe reveal how time behaved. When everything was compressed into a tiny, hot state, every discovery pushes us closer to understanding whether time is fundamental or emergent. What becomes clear is this: time is not the steady ticking background we once imagined. It bends, it stretches, it slows, it fractures. Our everyday experience hides this complexity because we live at slow speeds and moderate gravity. But the universe operates on rules far stranger than intuition allows. And this leads to a question that refuses to go away. If time can slow down, if different observers experience different presents, if the future already exists in space-time, does that mean time travel is possible? And if it is, why does the universe seem determined to prevent us from changing the past?